Thanks, Christine. I'll say that this is also my abstract. If any of you went looking for one, you actually found a different title. Part of it had to do with me deciding what exactly to talk about, and the breadth of this particular community was one of the reasons that gave me pause as to what I wanted to cover. So what I'm going to talk about is climate mantle coupling. That was what I was asked to talk about, but in particular, the issue is how do you build and maintain an atmosphere? And that really comes down to how volatile cycling works, and how volatile cycling works in terms of how much atmosphere you produce or maintain has a lot to do with whether habitability is even possible. And so volatile cycling, to talk about, has a lot to do with whatever the tectonic regime of Earth or any other planet happens to be. So how the planet stirs itself has a lot to do with whether we keep an atmosphere, whether we can have a habitable period, and how dynamic that period is. So habitability is not a state property of a planet. It's very much a transient. In the exoplanet community, this issue of habitable zone, that's the only time you'll hear me use that expression, is a big deal. And they look for it. It's almost like a hunter looking for a target. What I show you today is that if there's any wrong way to think about that problem, that's the way. There is no habitable zone. It's a very dynamic property. And Adam Burrows, there's a series of review papers on the sort of state of the world in exoplanetology a couple of years ago, and he kind of hinted at it in basically pointing the direction of inquiry into what is the nature of planetary atmospheres and how do we use them to understand planetary interiors. Where he went with his paper was going, okay, so if planets evolve over time, then our atmospheres evolve over time, then habitability evolves over time. So the idea that Sun-Earth distance, for example, is the major control is probably misleading at the best of times. Okay, in any event, I'm going to be focusing on terrestrial planets, and we have 3 of them, at least for today: Mars, Earth, and Venus. And the volatile cycling comes down to the sort of 3 things that enter. One is, what's the tectonic regime? How does the tectonic regime affect or how is it modified by volcanism and weathering? And then climate. So again, or not again, I guess in more detail, if we break this out a little bit further, there's a lot involved in each of these 3, I'll learn how to drive this at some point. Each of the 3 monikers. The tectonic regime, I'm going to be focusing on mantle stirring and structure, mostly stirring. So what is the stirring style? How does ingassing and outgassing work? Tectonic regime, it depends on planetary size a bit. It's affected by and affects melting and volcanism. Where does the mantle melt? How is that melt delivered to the surface? Stirring is affected by crust production. Where does that happen? Continents, supercontinents, they can add stiff bits to the top of the mantle, which can introduce transients to the way the planet stirs itself and also affect whether it can stir itself. The weathering regime. Weathering is not just about temperature. It's about how do you turn rocks into clay, and the first part is a mechanical one. And the mechanics of weathering varies depending whether we're at subduction zones or even at mid-ocean ridges. Seafloor weathering is for real. But it also happens in continental interiors. Second part, volcanism introduces greenhouse gases and aerosols. So the atmosphere, its radiative properties is a strong function of volcanism, which is obviously tied to the way the mantle melts. Weathering is affected by volcanism again by volcanism determining what rocks are around. If most of the volcanic rocks are basalts versus, say, granite, then the weathering potentials become much different. Volcanism can introduce hazes, so aerosols are one can introduce hazes, aerosols. It can introduce hazes, particularly in a low oxygen world. So volcanic products can lead to the formation of black hazes, of white hazes, all kinds of things, which affect the climate, which in turn affects the potential for habitability. Crust production, obviously that enters into albedo, and that has a big effect on what the average surface temperature on Earth is and how that varies in space. Okay, and in volatile cycling climate, obviously climate depends on surface temperature. There's all kinds of feedbacks. Albedo depends on surface temperature, depends on whether we have life, whether we have rocks. Weathering again. So weathering here certainly depends on temperature, precipitation rates. So weathering, let's say a function of precipitation rates. Whether you get precipitation depends on whether you're making mountains and where those mountains are. Are they in the tropics? Are they in high latitude? And so on. So the point of this anyway is to indicate that the volatile cycling that governs Earth's climate or any planet's climate involves a number of different things that are very tightly coupled and also complex. So there's lots of opportunities for feedbacks and rich behaviors. The idea of thinking about habitability or habitable zone, I think the idea of thinking about habitable zone is sort of very, I would say, too restrictive. Thinking about all these three main controls on ingassing and outgassing and atmospheric stability, the issue is, do we get habitability, if that's what the question we're interested in? How long does it last? I guess for the purpose of this symposium, to what extent does that enable habitants as well? Okay, some issues that enter into the style of volatile cycling. So I'm going to be sort of focusing mostly on mantle stirring, how that works. Planetary formation. So what is the budget of heat-producing elements in the mantle? Or where are the heat-producing elements? At the top of the mantle? Are they at the bottom of the mantle? They're stuck in the core. Planetary age, internal temperature of a mantle, so we'll talk about a bit, has a lot to do with the potential for a given tectonic regime. And age has a lot to do with, well, the strength of radiogenic heating. So young planets have different heating rates than old planets. The big one, history. What is the history of tectonic deformation, tectonic motion? It turns out that the evolutionary path a planet takes depends on where it's been. It's a bit like humans, I guess, in that way. That depending on how we spend our teenage years, we end up as a professor or not. On my teenage years, I can say nobody would have guessed I'd be a professor. Most of what I'm going to show you, the tectonic, particularly with the tectonic regimes, we get plate tectonics, not plate tectonics, something in between. All those solutions are usually permitted. Say that again. Mars, Venus, our Earth solutions for an evolutionary path are all almost equally plausible at the beginning of Earth's time. So how did Earth end up the way it is? It is not a foregone conclusion. Tectonic resilience. So Earth ended up in a plate tectonic regime and managed to stay there. That is a kind of amazing thing. So what controls the resilience of that particular attractor? Okay, a few broad questions which you can read faster than I'm going to say, but which are beyond my talk. They're sort of partly for discussion. So is the habitability that has lasted so long a natural consequence of Earth's current tectonic regime? Is our current Earth some product or somehow related to an early crisis? Impact history or impact erosion. We'll do a thought experiment related to that. So do the very initial conditions enter into where we are now, and how does that work? Is our current tectonic regime and climatic resilience a product of the way we started and how we evolved along that path? So is the memory of the beginning of plate tectonics, for example, or the way in which the first magma ocean solidified, the rheological structure that emerged from that, has that played a big part in leading Earth to where it is? And then finally, what are the big links between the Mantle dynamic controls on the probability for habitability and inhabitants themselves? And I'll show you an example. I don't have enough time to do the thought experiment I want to do, but one question is, to what extent does long period tectonically driven changes in climate impose environmental stresses that are expressed in the biological record? And we'll look at one example in a moment. But what I do today is talk a bit about how you write this problem down. So what are some of the underlying mechanics that go into thinking about the tectonic regime of a planet, the way it stirs itself, the major control in ingassing and outgassing. And then we're not going to do 3 thought experiments. I hope to get through 2. The first is a simple one. If we throw rocks at Earth early, right after the magma ocean finished solidifying, assuming there's a bit of crust on top. If we lose that crust to space, we lose some heat production. Does that put Earth on an evolutionary path that is more likely to end up in the regime we're in now, as opposed to, say, Venus? One we're not going to talk about, but it's interesting to think about. If anyone's interested in talking about it, I can offline, but this is a huge one. So intermittent transients, supercontinental cycles, lock up the Earth. I'm going to show you a simulation of one in just a minute. They lock up the way the Earth stirs itself. And the question is, can they drive climatic crises like Snowball Earth? And the answer is yes, they can. At least we have models that do that. And at least in the cryogenian, the last Snowball Earth produced a biological opportunity, to show you in just a moment. The one I hope I do get to is the more interesting one, I think, for sort of the general picture for how terrestrial planets work, which is how resilient is the climate of Earth to time dependence in Earth's tectonic regime. That is evident in proxy data I'm going to show you. All right, so first thing I'm not going to talk about, just because it's interesting to think about. So time on the x-axis here. So this is 1.6 billion years ago. This is now. And what you're looking at, the blue bar, if you can't read it, this is Snowball Earth. This is about 740 million years. That's 605 million years at the other end. And what you're looking at are a few different lines. The blue is the rise of oxygen. Green is total biomass. So a billion years up until the end of the cryogenian, the world was dominated by single-cell dudes. They had a good time, right? They ran the show for a billion years. The end of the meltout, which, by the way, happened during the breakup of Rodinia. 5 million years is about how long it took for the essential diversity we see now to begin to emerge. 5 million years after a billion years of stability. So the question that we don't have time to talk about is, to what extent did the formation and breakup of Rodinia affect climate and affect the structure of the oceans, possibly to give rise to the environmental stresses that may have given rise to this change? Whether it's an instability or an expression of bistability, I don't know, but it's interesting. Okay, do plate tectonics stir Earth smoothly, continuously? Okay, raise your hand if you think they do. Plate tectonics is always taught as being this slow, gradual thing. So who are the students in here? Raise your hand. Oh, there's one student in here. Okay, who's not a student in here? All right, everyone who's not raising their hand. So how does plate tectonics stir the Earth smoothly? I got a laser pointer. I'm pointing right at you. No, I was behind you. That's it, you. You are now, but okay. But does plate tectonics stir the Earth smoothly and continuously? He's the professor, right? I don't want to answer the question. All right, I got to move on, otherwise Christine will get to me. So the answer is, it's interesting, right? That's another professorly answer. 4 billion years ago now, these are a bunch of different proxies for internal and external dynamic, or solid body dynamics of the way the Earth works. Did I kill it? No, maybe. The first plot, plate velocity. This is apparent plate velocity. This is using paleomagnetic data and ages to get at relative motions between plates. And what you see is you go back through time and there are peaks. There were where relative motions are fast and slow. Paleomagnetic intensity. John's probably talked to a number of you guys about this. The dipole moment has varied a lot in time, and it has almost killed the laser pointer. High, low, high, low. Those variations are getting more robust, not less, as time goes on. Passive margin longevity. Who knows what a passive margin is? 2 people. 3 people. Okay, what's a passive margin? John. Okay, it's boring. Nothing much happens. Okay, where passive margin longevity is long, often metamorphic gradients, well, when passive margin, is long, often metamorphic gradients are, well, lowish compared to the peak. These kinds of data are sort of interesting. So where you have nothing happening, you don't have a lot, basically the gradients through continents are very low. Where you have a lot happening, the passive margin longevity is very low. We have steep metamorphic gradients. So in this particular case, there's lots of heat transfer continents are getting beat up, formed, destructed. Lots of heat transfer through the continents, so no passive margins. They're getting eaten up. Right? So the evolution of Earth's continents, or you can think of as Wilson cycles, though they don't exist yet, is increases and decreases in passive margin longevity telling us about periods where the Earth is very, very active tectonically and where it isn't. Komatiites will leave alone. Magnesium, so people talk about the Earth's mantle getting warmer back through time and magnesium being a proxy. Well, yeah, it's high back through then, but it oscillates. If you look down at what's called osmium depletion ages, which are of cratonic sulfides, which is a way of dating when you build cratons, the production of cratons, the oldest part of continents, again, it happens in peaks. A whole bunch is built 3 billion years ago, then 2, etc. So the picture here is time dependence. Thank you. The time dependence is played out in other ways. So this is another example of that time dependence. So this is now, and that's 3.5 billion years ago. The colored bars are the ages of gold deposits. Who thinks about gold deposits in this room? Anybody? One person. All right, Mark Hirschman thinks about gold deposits. But you see, you go back through time, is the production of gold is periodic. Or not periodic, but intermittent. Superimposed onto that, this line in the background are zircon ages. These are zircons form at about 800 degrees in granites. So they're related to the production of granites, which are parts of continents as they form. So they're related to core complexes and so on. So we're looking at is the production of crust happening also in time-dependent ways. Gold deposits are time-dependent. Crust happens in time-dependent ways. What about climate? Subject to what I'm talking about today. So one of the biggest mysteries as you go back through time is, the cryogenian snowball Earth is here, 600 million years ago to 742, thereabouts. The one background 2.3 is hotly debated. One of the big mysteries is why the Earth did not have profound glaciation early on when the sun is weak. Right? So episodic tectonics has somehow modulated Earth's climate to produce glaciation only relatively recently, or episodic behavior anyway, early. All right, is the time dependence a surprise? Now again, at the beginning I said, okay, the way volatile cycling works, the major control is, well, how does the mantle stir gases into itself and relieve them? So to make this point, we're going to watch a movie. And this is a numerical analyst's view of the current continental distribution. So I guess this is for Tobias Hoink, well, basically Africa. Highly pixelated. So the first 3 movies are different ways of looking at continents. These are plate boundaries, horizontal velocities, and strain rates. The bottom is heat transfer. Temperature, this is plates going down and plumes rising. So in each of these simulations, the middle is the core, it's hot. The top is cold, there's an asthenosphere, and the plates are strong. Just want you to watch the movie, thinking about the fact that it's all outgassing and atmospheric production is all about stirring. If you look at the interior mantle, everywhere you see an upwelling, that is where volcanism is happening, crustal production. You can see in the continents and in the responses of the plates, there's an inherent time dependence. What we're looking at now is continents slowly forming up to form a supercontinent. And they bounce around, they wander around until they locked up and they get stuck here. Now this is 1 billion years of Earth history in a few seconds. But the key thing here is that in this particular simulation, which is relatively high-end in terms of what's in it, including plates, a fairly complex rheology, and just letting the Earth do what it does, there's an inherent time dependence. Okay. Now, some basic mechanics. So mantle stirring and volatile exchange comes down to breaking plates and moving them around to start with. And so we look at 2 concepts. First is to break a plate. If you imagine growing a mantle at the end of the magma ocean period and having a lithosphere on top and forming a drip beneath it. To break a plate, flow into the drip forming beneath a plate or a lithosphere, has to pull down on that plate enough or strongly enough to actually break it. So what matters is how fast the drip is going and how viscous it is. So in this particular case, the drip has a Newtonian rheology, looks like this. It has to outdo a yield stress. The yield stress depends on a number of things. Depends on what the volatile budget is and what the lithosphere is actually made of. And then the speed of the drip also matters. So this particular picture, which is relatively naive, if the drip falls down and can break a plate, well, then we get plate tectonics to start, and we can go from one plate to more than one. And the key issue is how big is this viscous stress? A sort of more interesting and deeper picture is to realize that as we pull down on the plate, we do some deformation at the top. So as soon as we have deformation at the top, there's topography here, so this area is higher than this. And so there are lateral differences in hydrostatic pressures. This topography is enabling lithosphere that's over here to try and flow in to fill the gap. So there's one restoring force that enters the problem. As we pull down on this at some rate, there's a rate at which flow of the lithosphere into that gap is trying to anneal the boundary. These dashed lines are an attempt to show you the other part, which is microstructural damage. As the plate pulls down on a lithosphere and changes the fabric, there's memory of that fabric. So the two other issues that enter is, well, are we pulling down on this fast enough to keep this plate boundary open before it heals itself? And that can depend, the healing rate can depend on temperature, composition, volatiles, and history. And what is the memory of this damage? So we're introducing damage, and how does that affect the way that the mantle moves, or the mantle evolves beyond that? Okay, so very quickly, an overview of some of the basics. So stagnant lid, one-plate planets happen where the pull-down stress, the convective stress, is less than the lithospheric yield stress. Basically, the drips can't pull down and break it. The convective stress declines with increasing mantle temperatures. The more heat production, for example, we have in here, the less this is. If the stress that we're pulling down with equals the yield stress, well, then we can go either way. So this is the sort of basic condition for an episodic regime. If the convective stress is bigger than the yield stress and we can maintain it that way, then in principle we can have a plate tectonic regime. Convective stresses are very sensitive to temperature, as I've mentioned. And yield stresses are very sensitive to the volatile budget. Okay, now, a more modern view. The problem with Earth is that direction matters in terms of how we do those experiments of breaking and getting plates to grow and break. This is a sort of beautiful, this is the end of a beautiful PhD by Matt Weller. And what this is a non-dimensional internal heating rate on the y-axis and a yield stress on the left. So this is the strength of plates. And if I choose one, and we do an experiment where I ask the question, if I begin in a stagnant lid regime in this case, and I increase the internal heating rate, or I move up in internal heating rate space. The transition to stagnant lid, if I begin here and go up, happens down here. If I begin the same experiment at high heating rates and decrease the heating rate, let me back up and do this again. The regime diagram here, so we've got several different modes. Stagnant lid, one plate. Plate tectonics, multi-mode is both plates and not plates are possible. If I choose a lithospheric yield stress and I increase, I move up the internal heating rate. The transition, or where the transition from stagnant lid to multi-mode behavior happens at a different location in internal heating rate space than if I run the experiment the other way. So there's a directionality to this and a bit of hysteresis. If you look at it differently, in terms of a biostability diagram, so up here we've got a number of things going on. So one is the condition that we're going to play with, the tectonic states of stagnant lid and plate tectonics, and a convective vigor. So if I begin with no plate tectonics and I go this way, I can be in either a plate tectonic or a stagnant lid regime. What the simulations suggest, what the plot shows, if we now project this back down onto a surface at the bottom, is if I begin in a stagnant lid regime and I change the experimental condition, let's say increase, well, let me do, I'm going to change things. Let's just look at surface temperature. Okay, so great. All right, let me, okay. So one of the ways we can turn plate tectonics off is by making the surface, let me just come back to this cartoon. One of the ways we can close up plate boundaries is by making the surface warm. So if I increase the surface temperature of the planet through greenhouse forcing, we increase we change the temperature of Earth's surface by say 10 or 50 or 100 degrees by greenhouse forcing. We make the top of the lithosphere more runny, and we have a better chance of annealing that particular boundary. If we go at looking at this particular situation, if we begin in a stagnant lid regime, which is this red dot, and I decrease the surface temperature. So in principle, I'm increasing the ability to keep a plate boundary open. What you can see is we never actually get out. If I begin in a plate tectonic regime and I increase the surface temperature, we get an easy way, we get a transition to stagnant lid. So what the point here is to show is that depending on which way we begin, if we begin in stagnant lid, it's not super easy to get out. If we begin in plate tectonic mode, we can get into a one plate regime, but it's very difficult to get back from that. Okay. Now, how much time have I got? All right. So quickly, a couple of thought experiments. So the first one is what happens if we reduce the heat production in Earth a little bit by pelting it with rocks early. So this is basically making the mantle temperature on average a little bit colder. If we begin, in this particular case, if we begin with a chondritic planet that in most of our simulations at early times tends to want to be in a stagnant lid regime, and we reduce the amount of heat production, an amount that corresponds to losing what is essentially the modern inventory of continental heat production, there is a greater probability to end up in a multi-mode regime. Right? So the early erosion of Earth by rocks, essentially, by big rocks, makes it more likely to end up in a regime where plate tectonics is at least possible. If we do the other experiment, we begin in this world and we begin in a plate tectonic regime and we increase the heat production towards something like chondritic, we're more likely to be in a stagnant lid or one plate planet world. So the idea here is that the style of stirring, the choice a planet makes, depends in this case on how strong the convective stress is. And that depends a bit on the collisional history early. All right, quick one, I promise. All right, so next thing is what happens if we take, the data set I showed at the beginning, this one, basically said, all right, Earth's first 3 billion years certainly was dynamically very active, very time dependent. The question is, how resilient was Earth's climate through that period? As Earth was figuring itself out, as it was evolving, if we go back in time, evolving from where we have sort of continuous plate tectonics to something that looks more spasmodic. What are the consequences? One way to do this is to perturb a thermal history model. So what this is this is back in time. It's a thermal history calculation for Earth with some other stuff on it. So the black line is the evolution of mantle temperature. As we go back in time, Earth's plates choose different shape, different planforms, and the amount of the way in which it cools changes. So black is the temperature of the mantle. The outgassing rates are in the heavy red lines. So the heavy line, this is just assuming Mark Hirschman's solidus is right. And the dashed red line is assuming that Mark Hirschman's solidus is right and his student Raj Das Gupta's outgassing efficiency is correct. So outgassing changes back through time because decarbonation is better. So we can choose a period and perturb it. So if we take the mantle temperature and now introduce an episodic component to it, we can ask the question, what is the PCO2 that emerges from that? The PCO2 depends on the volcanic flux and the weathering regime, the weathering rate. I'll just show you a couple solutions, and then I'll finish. So we're going to look at a couple plots that look like this. So this is a zonal energy balance model, and so you're going to look at greenhouse forcing. All right, I'll jump to the end. Okay. All right, so we're going to perturb it. I'm going to ignore Christine for 10 seconds. So the three different possible solutions: ice-free, snowball Earth, partially glaciated Earth. This is where we start. If we introduce that perturbation under Earth's current mantle temperature, what you can see as we go through the hot period, we head towards an ice-free Earth. We don't approach a greenhouse runaway. As we go through the cold period, we just make more glaciers. Not super interesting. If we go at 3.5 billion years, the answer is potentially a lot more interesting. In that at 3.5 billion years, we essentially begin in a frozen planet. So this is 3.5 billion. We begin in a frozen planet. If we warm the planet up, we can actually achieve partial glaciation. We could actually end up all the way up over here. If we cool the planet back down, well, we just make a frozen planet a lot more frozen. In the Precambrian world, which is a water world, the albedo is that mostly of a water planet. The interesting thing here is if we increase the outgassing or decrease the outgassing, we never enter a panglacial Earth. Right? So Precambrian world being warm, at least with our simulations, is not a surprise.
It's been a few more than 10 seconds.
Yeah, that's it. Okay. All right, so just to finish, volatile cycling, tried to fit too much into this, but basically the crux is mantle stirring. How does ingassing and outgassing work? How does it in turn govern the atmospheric stability? How does that affect the radiative properties of the atmosphere? And what is the likelihood and duration of habitable periods? In terms of Earth, we can bounce in and out of snowballs, but we don't seem to do much more than that.
All right. Thank you. All right, let's thank our speaker, please. So I guess we have a short time for questions, and you can catch Mark maybe at the poster and coffee breaks. Yes, please.
Yeah, could you go back one slide, please?
Sure.
Now, that plot on the left, there's for example, just the blue lines where we're talking about snowball events. Now, there's a lot more structure in the last billion years than there is previously.
Yes.
And I assume that that's a selection effect, but can you make any comments about that? For example, you have this, what's called the boring billion, I guess, where there's nothing there. Now, did a lot happen and we just can't see it because of selection effects and preservation biases, or what?
Well, I don't think you can get away from the problem of selectional bias as you go back to the Archean because there's not a lot of rocks around. However, in the exposed Archean rocks, Proterozoic and Archean rocks from 2 billion years and before, there's only one period, this one in particular, that has reliable glacial deposits in it. So there's no drop stones. There's no evidence of cap carbonate-like sequences that are common indicators of rapid meltouts from snowball solutions. But there are no reliable glacial features in any rocks. Certainly before, this guy is hotly contested. This is Paul Hoffman's figure. Before 2.5 is, basically all glacial features before that are questions of debate.
Right, but could there be lots and lots and lots of structure there, as much on the right side of this plot as on the left?
No.
No.
So to produce these two periods took lots and lots of first you have to identify all the rocks on the planet that are within that age group, and they're in the Mackenzie Mountains in Canada, in Africa and in Australia. And in those, the question you ask is, what is the areal fraction that records evidence of not just glaciers, but rapid deglaciation? You have to be able to demonstrate that the glaciation was also at the equator. And there's directional paleomagnetic data here that allows you to do that more convincingly. But there's lots of rock that is thought to be at high latitude at these periods with no evidence of glaciation. Okay. Not true. I'm not going to make, I am spouting the party line then. So not true. What is your... This one is. Yes. I'm not arguing at 2.3.
But you said the whole thing wasn't.
No.
There's another potential one at 3.5 that Martian DeWitt published about a year ago. Very clear drop stones, no evidence of a cap, but we don't really know if a cap carbonate would form under the conditions of an Archean ocean. The chemistry is different.
Chemistry is different. So the drop stones
but
were inferred to be...
There is what looks like a good glacial thing in the Barberton at about 3.5. Clear drop stones, varved units, no striated pebbles, but you don't always get those.
True enough, but what you don't see is continuous evidence of glaciation all the way through this period,
but
even partial.
But you know, the record is not commensurate to that. Full stop. We don't have a continuous record of Archean time the way we do with the Phanerozoic.
2.9? 2.9 for glaciation or for global glaciation?
No, difficult to demonstrate global, but at least some place Pongra glaciation is present south.
Okay, but you would, I mean...
If you, for example, if you would like to discuss a global, but you know, percentage of Archean, specifically late Archean genus, occupy only 20% of total continents.
Sure.
And if we go back early Archean, it's less than 1%.
Oh, I'm not arguing with that. But so
Yeah.
the model solutions that we have admit partial glaciation through that whole period.
So that therefore that is positive, at least one.
Oh yeah, I wouldn't argue that there's the surprising thing in this period is that there's not global glaciation the whole time. Right. So if I did a climate model without considering the geodynamic control on volcanic outgassing and weathering, we would have a snowball solution for the first billion years of Earth's life. If I include weathering and the outgassing as is controlled by mantle stirring, we get partialized solutions. And I don't think that's inconsistent with either of the two comments.
All right. Any more questions? We seem to still have a bit of time, but all right. Well, then we'll go ahead and move on to the next talk. Thank you, Mark.